Hello everyone, my name is Jiahao Xu, and today I'm going to present our work titled CNN-LSTM Average Fusion Network, a sentiment analysis model based on multi-feature fusion. My presenter ID is 33, and our paper ID is 109. In this presentation, I will briefly walk you through 5 main parts: introduction, proposed model, experiments, results, and conclusion. Let's begin with a brief introduction. Today, we are witnessing an explosion of user-generated content across social media. This massive volume of text data provides rich opportunity for sentiment analysis. Sentiment analysis plays a crucial role in analyzing public opinion, enhancing user experience, and informing business strategies. However, traditional machine learning methods, such as SVM, mainly rely on handcrafted features. They often struggle to capture the deep and subtle semantic informations in complex natural language expressions. Today, deep learning models, especially those utilizing CNNs, LSTM, and pooling techniques, offers powerful capabilities to automatically learn multi-level semantic patterns from raw data, significantly improving the effectiveness of sentiment analysis. In this study, we define sentiment analysis as a text classification task. Especially, we aim to categorize input text into 6 basic emotions: joy, fear, anger, sadness, surprise, and love. However, the nature of human language introduces significant challenge. First, there is a semantic ambiguity. The same phrase may carry different emotional meaning depending on context. Second, emotional expressions are highly diverse, and the same emotion can be conveyed in many different ways. To overcome these challenges, our objective is to develop a robust, multi-feature model. Such a model needs to simultaneously capture local semantic patterns, sequential contextual relationships, and global sentiment trends, providing a comprehensive understanding of the text's emotional state. Here is our network, which starts by converting tokenized text into dense word embedding, providing a meaningful numerical representation for each word. It then applies 3 parallel branches for each of feature extraction. The CNN branch uses one-dimensional convolutions to extract local features, identifying local patterns such as emotional phrases. The LSTM branch captures sequential dependency across the text sequence from both forward and backward direction, model the contextual flow of emotion. The average polling branch calculates the mean of all words embeddings, summarize the global semantic meaning of the text. After extracting these diverse features, they are concatenated into a comprehensive feature vector. This fused vector is passed through a fully connected layer and a softmax activation to produce the final sentiment prediction across 6 categories. For our experiments, we use emotions for an LP dataset from Kaggle, which contains text samples labeled with 6 basic emotions. The preprocessing pipeline consists of 4 steps. First, we clean the text to remove special characters and extra spaces. Second, we tokenizing words and constructing a vocabulary by keeping only words whose frequency exceeds a certain threshold. And finally, we converting text into a sequence of word indices and applying patterns to ensure uniform sequence lengths. To better understand the corpus, we also generate a word cloud visualization, which highlights the most frequent words in the dataset. For training, we employed the cross-interface loss function, and we also use a DAM optimizer with the initial learning rates to achieve fast and stable convergence. To prevent overfitting, dropout regularization was applied in the fully connected layer. Additionally, we implemented learning rate decay and early stopping based on validation performance. All experiments were conducted using PyTorch framework on machine equipped with NVIDIA GeForce RTX 38 GPU. Our proposed model achieved an accuracy of 88.20% on the test set, demonstrating strong overall performance in the sentiment classification task. The training and validation loss curve shows a steady decline over epochs, while the accuracy curves consistently rise and eventually stabilize. This indicates that the model successfully converged without significant signs of overfitting, confirming the effectiveness of the training strategy. The confusion matrix provides a deeper insight into the model performance. The model performs best on the categories of joy and sadness, achieving accuracy of 93% and 91%. However, it struggles with surprise category, achieving only 59 accuracy. This result suggests that while the model captures the most emotional expressions effectively, distinguishing emotion with overlapping semantic patterns like surprise and fear remains a challenging task. To further evaluate the effectiveness of our proposed model, we conducted both baseline comparison and ablation experiment. In the baseline comparison, our model achieved an accuracy of 88.20%, outperforming several strong baselines such as the CNN, which had 82.55%, LSTM at 84.30%, and so on. Moving to the ablation study, we analyzed the contribution of each feature extraction branch by systematically removing different components. When using only CNN, the model achieved 82.45%. Using only LSTM resulting in 84.13%, while relying solely on average polling lead to a much lower accuracy. This result confirms that integrating local, sequential, and global semantic features significantly boosts model performance. Each branch contributes uniquely to the final outcome. In conclusion, this study proposed a sentiment analysis model based on fusion of CNN, LSTM, and average polling features, which outperform other baseline emotions datasets for NLP. For future work, we plan to incorporate a attention mechanism to better focus on key sentiment words and phrases. We will also evaluate the model on diverse datasets, including short text TOEFL, to validate its capability. Another direction is to address the imbalance problem by improving the recognition rates for rare classes such as surprise. Finally, we aim to conduct a detailed computational efficiency analysis and explore integrating lightweight pre-trained language models to maintain high performance while improving inference speed and reducing model size. Thanks for your listening.